Okay, so as usual, if you're not hearing me or you need clarification on anything, feel free to interrupt at any time. If you put it in the chat, it may take me a little while to notice it. All right, so better if you say something. Right, so today we are continuing and concluding our discussion on active filters. Last week we saw, on Monday we spoke about the first introduction to it, which was the simple low pass and high pass filters, the first order filters. And then on Tuesday, we took a look at expanding the response or increasing the response of the filters to make the cutoff frequencies sharper than the original first order. And then if you tie it back with what we did this morning in the other class, we spoke specifically about the rate of the roll-off, that the single order filters cut off at 20 decibels per decade, and the high order, in our case, the second order filters cut off at 40 dB per decade. And we ended by designing last time a second order filter, a particular type of second order filter called the Salin-Key filter, where you took the first order circuit that we had designed and you added one additional resistor and one additional capacitor. And if you did that for the low pass, you created a second order low pass. The high pass, of course, you swap the resistors and the capacitors, and then you add an additional capacitor and a resistor to the existing pair, and you get a second order filter that is a second order high pass filter. And we saw the transfer functions for both of them. We went through how to derive it, and I said the actual simplifying the equations will be part of one of the problem sets coming up that you could try. But the derivation, how to set up the Kirchhoff's equations to solve it, we set up those equations. The actual solutions is just algebra, and you just have to be careful what you do, because there are two resistors and two capacitors in it. And then if you made a particular assumption about the resistors and the capacitors for both the low pass and the high pass case, then the transfer function simplified into two fairly straightforward forms that you could remember. And one in particular was very close to something that we discussed in the signals and systems class, so you could remember that form. And then remember that the high pass filters always have an S squared in the numerator. In other words, the low pass filter of the types that we've designed only have poles, but the high pass filters have zeros and poles in them. And if it's a second order filter, it means you have two poles and two zeros for the high pass filter. If it's a first order filter, you have one pole for the low pass and one pole and one zero for the high pass. So somebody asked me a question at the end of the class last time, and I told him to wait for today because we actually will discuss part of that and then have a look at the other types of filters that we need to complete the whole spectrum here. Right, as we last time, what we did was to create a higher order filter by adding more passive components to the op-amp. In this case, what we're going to do today is that we can, as an alternative, we can create a higher order low pass or high pass filter by cascading first order sections. So in other words, what you have, you take one first order section, cascade it with a second first order section, right? So this is a low pass, this is a low pass here. And the net result is that this creates your second order low pass filter. And let's have a look at that. If I were to do that, we recall from the first slide last week, Monday when we did it, that the transfer function for our first order low pass filter was it's a single pole, so it's a 1 over SCR. Cascade that with itself basically, and what you get is a second order transfer function here. 1 over 1 plus 2 SCR, and look, the second order coming up here with the S squared. The cutoff frequency is 1 over RC. Remember, we define the cutoff frequency as the frequency where the amplitude of A j omega was equal to 1 over root 2. So when the amplitude of the frequency response. So you replace S with j omega here. Look at that. And then if you look at the frequency response of it, the point where the response drops to 1 over √2, that is where the cutoff frequency, we define that as a cutoff frequency. In this case, the cutoff frequency is going to be 1 over RC. Right? And you remember the cutoff frequency for each of these is 1 over RC. So the combined one is going to cut off at the same 1 over R times C. This is what the circuit, of course, will look like. So the difference here now is that we have 2 op-amps instead of 1. So you're now dealing with a trade-off. In one case, the filters that we discussed last week, Tuesday, had one op-amp and 2 capacitors and 2 resistors. Here we have 2 op-amps and 2 capacitors and 2 resistors. But the structure and the design is substantially easier. And of course, it's a lot easier to derive this type of transfer function than it is to derive the Sallen-Key type. Let's look and see if it works. Of course, the theory is fine, but you always have to test it out. We express it, of course, in the standard form. Remember, we spoke about that this morning. So the transfer functions, whatever transfer function you get like here, you always want to make the coefficient of S squared 1. So we're going to divide across the entire transfer function by C squared R squared. And we now get it into this form here. The cutoff frequency, of course, is, if you compare it to the standard form that we had before, omega C squared is 1 over C squared R squared, which gives us directly that the cutoff frequency is 1 over RC. And let's see an example where I put the cutoff frequency as 100 radians per second. So I pick R and C to make omega C 100 radians per second. And look at the response here. The first order, each first order filter will respond here according to the blue line. And the roll off, if you remember, was what? How many decibels per decade? Anybody recall? We did that this morning actually too, for those of you who were there. The single order rolls off at come on. Somebody, anybody? There you go, minus 20 dB per decade, correct. Right, so they roll off here minus 20 dB per decade. The second order, now we cascaded 2. So this now is going to roll off at minus 40 dB per decade. Right, notice the sharper roll off. And again, notice the phase relationship. We'll talk about that more in the signals class here, but the first order system has one pole and the phase goes from 0 to minus 90. The second order system goes from 0 to minus 180. Right, so that's a red line there. So here we have the 2 of them here, the 2 types of filters. One was the one that we discussed last week. One was the one that we just derived. You notice there are some slight differences in the transfer functions, and your job will be to tell which is which. Of course, you could derive it very quickly. And this is, of course, the standard form of the second order transfer function that we did way back when. So you could look at this. Once you get either of these functions in this form, then you could quickly compare the coefficients here to know what the cutoff frequency is, right? So in case which is which, this is the Sallen-Key here. And this is the cascaded. And if you compare the results here, look at the red lines on the left. Those are the ones that we just derived, the response. And look at the one on the right-hand side, which is this is the Sallen-Key here. For all intents and purposes, the results are the same. They look identical. There is one little subtle difference. If you look at the performance here of the Sallen-Key, right around cutoff, you'll notice that the cascaded filter gives you a little bit more of a rounded transition. Remember, this is the passband, this is the cutoff here. Passband, and the cutoff is the stop band, if you from our term stop band. Notice the transition for the passband to the stop band for the cascaded version is a little gentler than the transition in the case of the Salenki transfer function. All right, and that is one little disadvantage that you deal with. So if you were to cascade 3 of them, you would find that it would cut off at 60 dB per decade, but the transition here will be a little more gradual, right? There is a little bit of loss here. That, like most of the sort of design, there are always compromises between taking one approach versus another one. The cascaded one is substantially easier to design on paper. All right, but it is using an additional op-amp in the circuit itself, whereas the direct version does not. All right, so everybody following? Any questions on that? Or any comments that you've seen or you want to ask? Fine. Okay. And similarly, and this will be a little exercise as well, try the same approach for the high-pass filter. If you recall, the high-pass filter is something like S over 1 plus SCR. There's a 0 and a pole for the single order high-pass filter. So cascade 2 of these to give us now a second order high-pass filter. Sketch try sketching the frequency response for it and the cutoff frequency. Of course, the cutoff frequency is the same as the individual components, but you do the both of them and see what the response looks like. Okay. Right. So that takes care of the low passes and the high pass filters. And as I said now, creating higher pass filters now is just a question of cascading second and first order filters as many times as you like. There are ways of designing them with fairly complicated R's and C networks. And I'll comment on that down at the end when we speak about some final things here. But you can also, if you have, for instance, if you go and you're buying op-amps, you can get 4 operational amplifiers in one single IC packet, a very small packet, and it has 4 op-amps in it. So therefore, in one single packet, you could in theory design a 4th order filter without extra real estate or taking up any extra component space and so on. Right, so let's look at the other 2 filters that we still have to discuss. The first one is a bandpass. Remember what the bandpass does. It only allows signals in a certain range of frequencies to get through, and it rejects everything outside of this. That range is a band called a pass band. And this filter typically has a maximum output frequency at one value called the resonant or the center frequency of it. So the diagram below shows what this sort of behavior is. It passes some range of frequencies between omega L and omega H, omega L being a low frequency and omega H being a high. So that's a low frequency cutoff and a high frequency cutoff. And in the middle of there is a center frequency. And we'll see what the relationship between the 2 of them are. Right? We call the bandwidth of the bandpass filter the difference between the upper cutoff and the low cutoff frequency. If the filters, and this is a little bit of a spelling here, it's filter, F-I-L-T-E-R, so you could create that. If the bandpass filter is narrow band, it means that the width of the band is 0.1 or 1/10 of the resonant frequency. So like for instance here, we have, there's going from 0.1 hertz to 10 hertz. The resonant frequency is 1 hertz. If the bandwidth is 0.1 of that, then we call it a narrowband bandpass frequency filter. And those typically would give you a response looking like this. And then if the bandwidth or the pass band is bigger than 0.1 or 1/10 of the resonant frequency, we call it a wideband filter. And the wideband would be typically like what the blue trace upstairs are. It depends on the application. Sometimes, for instance, in certain types of scientific processing, for instance, like when you were doing a chemistry, you would have come across devices, at least if you didn't have them in the lab, devices called spectral, like infrared spectrophotometers and so on, that they use to analyze chemical compounds. Or if you like to watch those crime movies, you see them using it to analyze blood samples and the like. Those types of things, you have a lot of wavelengths to analyze. And in order to detect it, you need a very narrow bandpass filter to pick up one signal and reject the others. That's one sort of application of it. All right. The other thing would be in precise tone controls for audios where you want to just amplify or reject a particular very close band of frequencies in the audio range. That will be a function of it. The wideband tend to be used where you want to restrict, like for instance, for digital audio, the bandwidth of audio is 20 hertz to 20 kilohertz. So what I would do is that if I am processing audio for a recording of some sort, in a recording studio, you have the microphone set up in the studio. What you would do is to pass it through a bandpass filter that isolates this and sends this forward and rejects everything below or above. The below frequencies normally would not be heard, but it could be generated by equipment noise, air conditioning noise, and the like. The high frequency noise similarly could be generated by equipment, machinery working and the like. So as not to corrupt the sound, you would pass the audio through a wideband, 20 hertz or 20 kilohertz signal filter, that would basically extract the usable part here. And this is what you're going to process for recording. All right. And then just as a term, we're not going to use it much here, but you will meet it later on when you do network synthesis, for example. If you do take that course, there's something called the quality factor of the circuit, and it really describes how sharp this peak is. So a wideband filter tends to have a low Q. A sharp narrowband filter tends to have a high Q. Okay, and sometimes filter designers may, instead of using the term narrowband or wideband, may just say, okay, we need a high Q filter or a high quality factor filter, meaning that I want a narrowband filter. Yeah. Now, there are many ways to create the bandpass filters. And for instance, you could do the Salin-Key type, which is what we have here on the left-hand side. Notice here the resistor and capacitors are a little bit different. Or you could use particular frequency selective networks. We've met one already called the Weinberg. We use the Weinberg to make oscillators. But the Weinberg has a resonant frequency. So that this particular circuit, what it would do is to pass signals through, but only the resonant frequency of the Weinberg would be transmitted through, and then you get that coming out. Everything else wouldn't, the Weinberg would ignore, right? But all of them require a fairly complex set of analysis, and you'll meet some of this and the ways to design it when you do other courses like the network synthesis course, where Dr. Rock will take you through some of the designs that are used. Not all of them, but will introduce you to some of the more complicated designs. And usually at that point, you tend to use things like MATLAB to help you through with the analysis. We are going to take a slightly simpler approach because it's more of a one to make something practical that is usable and still understand the principles that are involved. So we are going to make it by cascading two first order filters, namely a low pass and a high pass filter. Right, so we will create it and we using a first order filter, a first order high pass filter. So this is one is a high pass filter and one is a low pass filter, and we're going to cascade them. Right, I'll leave you all to figure out which is which. You should be able to by now. So this is the expected behavior. The high pass filter, notice what a high pass filter does. A high pass filter rejects frequencies below some cutoff and passes everything above. The low pass filter passes everything below the cutoff and rejects everything above. So if I were to combine the two of them together, I would get, or I should get, a characteristic that gives me that sort of behavior, which is a bandpass behavior. Make sense? We have touched on this last time, but just to make sure, it sounds logical. Yeah, no, maybe. Let me know. Right? So, here are the things. The high pass filter determines the lower cutoff frequency, and the low pass filter determines the higher cutoff frequency. Why is that? This is the lower cutoff frequency here. This is the higher cutoff frequency here. The high pass filter determines omega L. Why? Because look at the shape of the characteristic. A high pass filter passes everything above a particular frequency. So everything signal is coming in here. The high pass filter will reject everything until its cutoff frequency reaches and then start to pass. So the high pass frequency filter determines the lower cutoff frequency for the bandpass. And then whatever is passing here now, right, when it reaches a particular cutoff frequency, we want it to reject everything higher than that. So this is the low pass characteristic here. But this also is the higher cutoff frequency for the bandpass. So in other words, the lower frequency is determined by the high pass filter. The higher frequency is determined by the low pass filter. Yeah? Clear? Make sure you're following it. Right. So from before, the low pass filter, the cutoff of the low pass filter is omega H. Remember, the low pass filter is this one. Right? So the low pass filter for that, you determine R1 and C1 accordingly to determine omega H. The high pass filter, this is the transfer function here. The cutoff frequency for that is determined by R2 and C2. And that determines omega L. So depending on what you want to design, you're going back to your circuit here, right? One of them is a low pass, one is a high pass. One determines the low frequency, one determines the high frequency here. So you set the two cutoff frequencies according to what we had discussed and developed last week. And then the overall transfer function, because it's a cascade, is the transfer function of the low pass filter multiplied by the transfer function of the high pass. All right. So if you do it, and I'm using, instead of having a set of C1s and C2s and so on, I'm using them in terms of the cutoff frequencies here, omega H and omega L. If you cascade the two and you simplify it down, you get that the transfer function for the bandpass filter is given by that expression down there. Notice it's a second order transfer function, right? It's a bandpass filter now, so it has 1, 0, and it has 2 poles in it. All right, this is just for information purposes, if you like, and just for observation. You always keep track of that. And again, there's a general form. You don't need to remember this. I'm just telling you this for information purposes. There is a general form for the transfer function for a bandpass. And you can either substitute the S equal to J omega here, or you compare it with the transfer or with the standard form. But the cutoff frequency, or the resonant frequency, sorry, is the square root of omega L by omega H. Remember we said that the bandpass has a low cutoff and a high cutoff, and there's a frequency where it peaks at, called the resonant frequency. That peak, the value of that is given by the square root of omega L times omega H. Yeah? Let's test the design. Right? Once you do these kind of things, it's always makes sense to try and test it. So we design a low pass filter, and the low pass filter, the cutoff frequency for the low pass filter is 100 radians per second, right? And the cutoff frequency for the high pass filter will be 1,000 radians per second. So this is how we're going to design the bandpass. So the bandpass, the lower cutoff frequency is 100, which is determined by the high pass filter. Right? This is determined here. I just put here because actually, I'll correct that. I think actually I should have put it for the other way around. Call this omega L, which is determined by the high pass frequency, and omega H, which is determined by the low pass filter here. Right? So make that little change for me. All right. So in fact, what I have here, the low pass filter cuts off at omega H. Notice the low pass filter is supposed to cut off at omega H. So I will make this change for you. I'm sorry about that. I have the wrong things on the diagram. The low pass filter determines the high frequency cutoff. So the low pass filter will cut off at 1,000 radians per second, which is this value here. Notice the blue line. So this is 1,000 radians per second. The high pass filter cuts off at 100 radians per second. That determines the lower bound. So this, the red line, is the high pass filter, right? Cutting off at 100 radians per second. Put it together, and this is what the overall response looks like. Right? My mistake here. Let me. This again, this is supposed to be omega L. This is supposed to be omega H. Okay? So that the overall response is the dotted line, which is what we want. A bandpass filter, the pass band is between 100 radians and 1,000 radians. So that's the pass band. So the bandwidth, if you like, is 1,000 radians minus 100, right? So the pass band is 900 radians, and the resonant frequency is the square root of 10 squared by 10 cubed, right? And that will give you this particular frequency here, the peak right at the middle here. Yeah. Everybody all right with that? Apart from my own typographical error. So when you look over the recording or you get your slides, change those two things for me. I will change them in time for tomorrow and I'll repost it online. So make sense? So it's very easy to make a band pass. You cascade a low pass and a high pass filter, and we get this sort of response here. Let's see if we could make a band reject filter the same way. Band reject filters do the opposite. So the response of the band reject filter looks like this. What this does now is to get rid of a particular set of frequencies that you don't want. I made an example in class last time. I told you if you've ever been in a situation with a public address system where it starts a high frequency wheel or the squeal, what they do is that most of the new systems have a filter that once it detects what you have is this happening, so you have a sudden resonant frequency occurring. So it creates a notch filter at exactly that, so that when the two are combined, the thing that is causing the feedback signal, that squeal, gets rejected. All right? And they use it for any number of applications. So for instance, as I mentioned, when you're doing biomedical work, there's a 60 hertz signal because we are in a 60 hertz power system, or 50 hertz, depending on where you are. We all pick up this 60 hertz signal. And if you just simply hook up electrodes, for instance, to measure brain waves or heart signals and the like, there is a 60 hertz signal always inside of there. So instead of seeing the signal, what you want, looking like that, the signal tends to look like this. The signal is riding a 60 hertz or 50 hertz power supply signal that you pick up because your body is picking up the electromagnetic radiation from the wiring in the wall and so on. What they do is that they would pass this now. You would take this and you would pass this through a notch filter that will remove the 60 hertz. So you want a 60 hertz notch here that will remove the 60 hertz signal and give you back the original things that you want. All right. In this case now, if we're using the high volt, the high pass and the low pass, we have to cascade them. Sorry, we can't cascade them. We have to put them in parallel. In other words, we have to have an arrangement like this. Now, why is that? Why I can't simply, I have a low pass and I have a high pass. Why can't I LPF H? Why can't I do this and get this sort of behavior? Anybody? Because I draw the diagram, it should be fairly easy to see. If I were to send a signal into the low pass filter will pass this. So this is what is going to survive from the signal. If this goes into the high pass filter, the high pass filter rejects everything less than this. So all of this gets rejected. So if I now pass that into the high pass filter, nothing is going to come out. Similarly, if I were to do it the other way around and put a high pass filter first, and then the low pass filter next, the high pass filter is going to do this. It's going to pass everything higher than a particular frequency. But when I go and pass this through the low pass filter is going to lop off everything here. It's going to pass everything here and lop off everything here. So again, you're going to get nothing coming off. So we can't do it that way. The cascades can allow us to create a bandpass, but in order to create a notch filter or a band reject filter, we have to put the low pass and the high pass in parallel. So this one, if you look at it, this will pass my low frequencies. The same signal goes through here and passes my high frequencies, right? And then at the end, I add them up. So I'm going to get that plus that being created. Yeah? Make sense? Yeah, no, maybe? All right. So the circuit arrangement is, again, to parallel the two of them. So this is, by now, you should be able to identify, this is a low pass filter here. This is a high pass. And you put it onto a summing amp, and we know you can make summing amps very easily with op amps. And as before. So we take the low pass filter and we create its own behavior, its own transfer function. So the notch now is going to be whatever is the transfer function of the low pass plus the transfer function of the high pass. If you do that, this is the low pass, this is the low pass filter here. This is the high pass filter here. So in other words, kind of that, right? You should be able to tell which one is which one. So the low pass transfer function and the high pass transfer function, add the two of them and you get now an overall transfer function looking like this. Again, the resonant frequency, just like for the band pass, the resonant frequency is given by the square root of the low and high cutoff frequencies. Right. This is easy to derive. It's a lot easier than the other approaches, so it should be easy for you to remember. All you have to remember is for the band pass, you cascade. For the band reject, you put the transfer functions in parallel and add them up. And of course, you test the response. So we let the low pass have a, in this case, my symbols are correct. So the low pass has a cutoff frequency of 10. The high pass has a cutoff frequency of 100. Put it into the transfer function. So this is the overall transfer function here. And if you plot the frequency response, look at the response that you get. Right, so this is the low pass behavior here. This is the high pass behavior here. And this is the band reject or the notch filter behavior. So by paralleling the two of them, we are able to get the behavior that we want. Check the resonant frequency. The resonant frequency here is supposed to be the square root of 10 by 10 cubed. So that should be 100. Look at the resonant frequency here, 10 squared. So this point is 10 squared, which is 100. Right, so the theory works. Right, now we'll conclude with a small discussion here on phase. Recall that when we have been talking about all of this thing, we keep insisting that the signals have a magnitude response, which is all well and good. But there's also a phase response associated with all of these and all transfer functions. Phase is almost as important as the magnitude response, because we said, for instance, in audio, if you change the phase, which is the time relationship between the signals, if you change the phase relationships between them, then the sound that comes out will sound different than what went in. And you can imagine if you are a singer, for instance, and how your sound or how your voice is sounding in real as compared to how when it goes through the recording process, the phase changes and your voice is sounding either at a higher pitch or a lower pitch, or in some cases, some of the notes that you're saying get canceled, right? So that is a very important consideration, and what you have to be aware of is that filtering removes unwanted frequencies. That is why you're doing the filters, but it does that at the expense of the phase relationship of the remaining components. So look at the diagram above. This is a band reject or the notch filter. So it passed through, and I use it to get rid of a frequency of 100 radians per second. But notice what happens to the phase of the signals as the signal comes through, as the phase approaches cutoff. There's a significant phase change from a minus shift to a positive shift. So in other words, some signals, remember, originally, if you were to just pass the signal through whatever processing it had, there would be no phase change. The phase would be nice and linear all the way through. You pass it to get rid of one frequency, but because of doing that, you have twisted up the phase relationship between them. And that is something that is very complicated to address. And that is why there are so many different types of transfer functions available. We have looked in what we did, we have largely concentrated on the amplitude response. So if you want to get a simple low pass or a high pass or a band pass or a notch or a band reject, as the case may be, that we create the response and we look at the magnitude response. But in many, many cases, the phase relationship also has to be preserved. And that is why you have to know, and this is a much more complicated process than just designing the amplitude response. You have to know what type of application you're dealing with. And each of these types of, these are, remember I told you, these are the transfer function polynomials, right? They are numerator over denominator polynomials that make the transfer function of the filter. We have been creating largely Butterworth filters for the most part. It has a reasonable phase response, except for certain types, like the notch filter that we just saw here, like this one, all right? So as you get more involved or you get specialized in this kind of thing, you have to make choices, and this is where the networks and so on change, and you have to sometimes use more passive components. And it is only when you are in it for a while that you will, and doing it for an extended period of time, that you get to know this kind of thing. All right, so that's just to comment on phase, and then to introduce one last type of filter that you will come across in communications, something called an all-pass filter. Now that seems kind of strange, a filter that passes all the frequencies. What it really does, though, is that magnitude-wise is passing everybody, but it does some changes to the phase. So it's sometimes called a phase shifter. And what you use is to use the filter to try to correct the kind of phase relationship that the other filters created. So for instance, a very simple example, look at this transfer function here, s minus 10 over s plus 10. If you were to plot the magnitude response for it, notice the magnitude response is flat all the way through. Tomorrow when we're doing both plots, we'll see that we will plot out an asymptotic plot just to show that the phase response, sorry, that the magnitude response looks like that. But look at the phase response. The phase response goes from plus 180 degrees to 0. If you were to check a filter that we did last time, and I'll just stop this sharing for a second and go back to something that we did last time. Look at this filter. This is a second order low pass filter, the Salinki filter. Look at the phase response. The phase response is going from 0 to to minus 180, 0 to minus 180. Ideally, the phase response should be this, flat at 0 all the way through. Notice it's going from 0 to minus 180. Let me stop this and come back to the example I just showed you here. Look at this filter. The phase shifter or the all-pass filter is going from 180 degrees to 0. So what we had just now, the second order filter that we had was doing this. It's going from 0 to minus 180. This one is going from 180 to 0. So if I were to take the output of the Salem-Key low-pass filter and pass it through this, the amplitude of the filter would not change because this one has a magnitude response that is 0 all the way through. So whatever the Salem-Key low-pass filter was doing will pass through unchanged here. This will not change it. But look at the phase. The Salem-Key filter does this. This filter is giving me the blue line. If I add up the two of them, what's going to happen? If I combine the two of them, right? So for instance, if I were to put this on this, right, or subtract it, put it that way. Let me try to subtract it. If I were to take this and subtract it from this, you would find that I could end up getting 0 phase shift all the way through. I could do it either way. I could do it, if I add it, I could get plus 180 all the way through. Or if I subtract it, I could get 0 all the way through. So by passing that response from the last type of filter through this, I could linearize or flatten the phase response as well. So I could get the best of both worlds. One is going from 180 to 0, the other one is going from 0 to minus 180. So between the two of them, I could either get a full 180 or a full 0. And a full 180 is just an inversion. A full 0 is no change. So I have two ways of doing it. Yeah? Make sense? So we use these kind of filters, the last time, the all-pass filter or the phase shifters, to sort of correct the behavior in some cases of our previous designs that we had. All right. So in summary, we looked at a number of filters. We looked at low-pass. First off, we saw that filters have basically 4 categories: low-pass, high-pass, band-pass, and band-reject. The low-pass filters, we looked at first and second order low-pass filters. We created the second order filters in 2 ways, by cascading first order filters. We did the same for the for the high-pass filters. We looked at the bandpass, and our particular approach was to create the bandpass response by cascading 2, a low-pass and a high-pass filter. One created a low cutoff, one created a high frequency cutoff. And then the last one is that we created a band reject or a notch filter by running 2 filters in parallel, a low pass filter and a high pass filter, and then we added the responses at the end. And then just to tie everything together, we had a discussion on phase that led us to just introduce and just briefly mention this thing called an all pass filter. The all pass filter has a flat magnitude response, so it's not going to reject or pass any particular frequencies. It's going to pass all of them. But what it does is that it shifts the phase. So in this particular one, it's shifting the phase from 180 down to 0. And if you put this with a filter that was going from 0 to minus 180, you could compensate depending on how you do it. You could either get a full 180 flat or a full 0 flat. All right? So that concludes our discussion on filters, active filters. And we have one more topic to discuss tomorrow, and that will conclude the theory course for ECNG 2012. All right, so we are finishing the course content tomorrow, and then from then and for the rest of the time, we will be spending time. You'll have some time to revise. I'll put up some problem sets, and we will go through those and review and discuss anything that people still have any issue with. I have started to mark the papers, and so far so good. There was a mistake that I made in one of the questions, so I'm giving everybody the full marks for the question because I realized that in the question there are a couple of ways you could interpret it, and people probably would have wasted time in the exam. So just to be fair to everybody going to get that question full marks. I'll tell you which one it is later on. But so far, so good. People seem to have done or are doing reasonably well, right? It will take a little while. I mean, the class, the number of scripts was 88 of them. So I'm going through it, but so far so good. So a few of you all will have a pretty good chunk of marks going into the final. The main difference, of course, is the final is closed book. So you're going to have to learn your stuff and be able to do a lot of this stuff from recall. So when I put up the next set of problem sets, and as we go along, when you are attempting them, revise the work and then attempt the question without looking at the notes. Try to commit the material to memory enough to solve the problem. I'm not going to ask you, I've already been hinting throughout the things that I expect you to do, to remember, the things that I expect you to be able to derive, right, straight off, and even in the circuits and so on, circuits that I will give you, circuits and arrangements that I expect you to be able to recall and draw. All right? Okay? So any questions before we close off this afternoon? All right, so let me stop the recording.